So I saved the notes so we could start from immediately where we were at the end of our last class meeting. So we had done a bunch of math in the frequency domain in order to come up with these two relationships for drive and sense mode displacements, where the drive mode displacement is just our transfer function h sub d multiplied by our force in the d direction, and this is something that we are going to be in control of. And then our sense mode displacement will be dependent on our quadrature error term, which I'm going to talk about that a little bit today, times our drive mode displacement plus our transfer function h sub s for our sense mode um, simple harmonic oscillator multiplied by our Coriolis force. So let's talk about that quadrature error thing a little bit first. Okay. So quadrature error is due to manufacturing issues. Okay. So ideally, it would be zero. And the drive and sense mode vibrations in our gyroscope would be perfectly orthogonal, so 90 degrees out of phase with each other, and we wouldn't have any issues. However, in a real device, we should expect to see some amount of coupling between the modes that occurs due to manufacturing variations. So essentially, if we had a simple system, and this is going to be a very dumbed down, simplified representation of a gyroscope. Here we would have a drive mode finger. Let's put another drive mode finger like so. Drive mode finger and a drive mode finger. And then internal to this would be our proof mass and all of that kind of good stuff, which I'm just going to simplify here as a little plate representing a mass with some fingers that we're going to use to do actuation, right? So here is our mass. Let's say that our direction for our drive mode would be up and down like so. So that's what drive mode would be. And if our mass experienced some rotation, then we would expect to see sense mode vibrations strictly left and right. Okay, so this is what we would happen under a Coriolis acceleration with no quadrature error. So if quadrature error were present, we would see something that looks like this instead. Okay, so once again, just drawing my simplistic representation of my fingers. And my mass system. Like so. And what we would expect to see due to the manufacturing error is that our drive mode vibrations wouldn't be perfectly up and down. So they might be slightly askew, something like this. Okay. which means that even under no Coriolis force, we would still have some amount of movement in the left and right direction that our system would erroneously consider to be an experienced acceleration, right? So that is the problem that we are trying to quantify and rectify, okay? So this would be our quadrature error motion. Error motion with no Coriolis force. So generally speaking, we wouldn't be able to do anything physical to this system because it would to fix this error because it would be cost prohibitive, right? So I don't know how familiar you all are with things like laser trimming microstructures and all of that kind of stuff, but it's a pretty lengthy process where you're constantly having to measure the quality factor of the device while you're effectively slowly removing material away to tune it to a very specific frequency and all of that kind of stuff. It is a very lengthy and time-consuming process that would never be bothered to do for something that's actually commercially available because it would make the part just too damn expensive. Unless you're the US military and then you do that shit all the time. But anyway, that's why they have their own clean rooms and all of that kind of stuff at their various research labs. So what a normal layperson would do would be to use a concept called electrical trimming. So essentially this mismatch um, or this motion that's slightly out of tune could be fixed by manipulating the voltages that we apply to this guy in order to make it vibrate only in the exact direction that we want to be. So we might do that by applying our normal DC actuation voltage here, and then we might have some small change in our voltage, and we would apply that exact same DC actuation voltage on this leg. And then on the opposite legs, we might do VDC minus some delta V and VDC minus some delta V like so, so that we are essentially attracting, actually, I guess I should have done it plus here and minus on the opposite side for the way that I drew the direction of movement. But essentially in a configuration like this, we would be trying to pull this leg a little bit closer to this electrode and pull this leg a little bit closer to this electrode, twisting it ever so slightly to try to balance out that erroneous motion from left to right. So this is what the electrical trimming process would entail. We would just have a very slight variation between those two voltages that we're using to actuate this thing, because if all of the voltages being equal cause it to go askew, then we need to capacitively attract one side a little bit closer to our electrodes in order to get our movement in a straight up and down motion. So that's how we would generally correct for quadrature error in a system like this. Okay, so now let's get back to our analysis of what's going on in a gyroscope, right? So we're going to assume from this point onward that we have corrected any quadrature error that we may have so that our sense and drive modes are completely orthogonal to each other. So let's look at our drive mode vibrations first. So typically, the drive mode of a MEMS gyroscope drawing the letter R got away from me. Is excited at the mechanical resonant frequency of the drive system. So the reason that we would do this is to essentially be able to induce the largest amplitude of vibration with the smallest amount of input energy going into the system, right? So if we look back up here, XD is equal to HD times FD. So if we look at HD here, what we're going to wind up seeing is that our transfer function will essentially be at its maximum when our actuation frequency omega is equal to omega naught d. Okay, so we're going to get the largest possible amplitude of our vibration, which we need because we want XS to be as large as possible as well. And we know that for XS to be large, XD also needs to be large. Okay. So at a frequency of omega is equal to omega naught D, the drive mode transfer function simplifies to HD, and this is for omega is equal to omega naught D, will be equal to negative J times 1 over MD, where this is the mass of our drive system, times QD over omega naught D squared. And that MD times omega naught D squared is literally just the spring constant of our drive system. So this reduces to just negative J times Q over K, like so. And from this, the drive mode displacement will be X sub D is H D FD, or negative J times QD over KD times FD. So essentially our displacement is 90 degrees behind our drive force. Okay. So the force that we apply probably through capacitive actuation will be 90 degrees out of phase with the displacement that we are seeing. Okay. In the sense mode, so if we assume quadrature error is 0, then our sense mode displacement XS as a function of omega will be HS as a function of omega times our experienced Coriolis force. And then we're just going to math this guy up real quick. So that's going to look like 1 over M sub S multiplied by omega naught S squared minus omega squared all over omega naught S squared minus omega squared quantity squared plus omega naught S over QS, that quantity squared, minus J times omega naught S, over QS divided by omega naught S squared minus omega squared squared plus omega naught S over QS squared. And then all of that would be multiplied by our Coriolis force, -2 times the mass of our drive mode system, omega, our rotation experienced, times our drive mode velocity. And this drive mode velocity here is just J omega times our drive mode displacement that we talked about above. Okay. So substituting that in, effectively, I'm going to be multiplying each of these terms by a factor of -J and then adding the other parts in. And so what that's going to wind up giving me is 1 over M sub S times twice M sub D X sub D capital omega squared omega naught S over QS, all of that divided by omega naught S squared minus omega squared squared plus omega naught S over QS quantity squared plus J twice MD XD capital omega lowercase omega naught S squared minus omega squared all over, oh, and actually I missed a negative sign out here, sorry for that. Omega naught S squared minus omega squared squared plus omega naught S over QS squared. Close my bracket. Do what? Yeah, so simple. Anyone could do this. So what I'm trying to bring to your attention here with this horrifying amount of math, and we are going to have a situation to where it can be simplified, and we'll talk about that here in a moment. But our sense mode displacement depends on the excitation frequency of our drive mode, because omega is the frequency at which we are exciting our drive mode. And so from this, we can develop two cases essentially to where this thing simplifies down, okay? And so those two cases are what are called matched modes, where omega naught S and omega naught D are literally the same thing. So the resonant frequency of both our sense and drive systems are equal to each other. Or we can have separated modes where the resonant frequency of our sense system is much, much larger than the resonant frequency of our drive system, so that we don't get any interference between those two types of vibrations. So let's look at match mode systems first, okay? So for a matched mode system, where omega naught S is equal to omega naught D, the sense mode displacement will reduce to xs as a function of omega will simply come out to be -2 times the ratio of md over ms times xd times our angular rotation omega qs over omega naught s. So in order for us to achieve large displacements, QS must be very high, and thus our system's bandwidth must be very small, since bandwidth and quality factor are inversely proportional to each other. Another downside of this particular method is that in order to get perfectly matched modes, it is likely going to actually have to have that physical trimming that is a costly procedure to make these resonant frequencies identical. For separated modes, where omega naught s is much greater than omega naught d, the sense mode displacement will reduce to xs as a function of omega will be -j twice md over ms xd omega times omega over omega naught s squared, which can be simplified down to -j times twice md xd capital omega lowercase omega over the spring constant of our sense mode system. So in this particular system, then, our sense mode displacement will actually lag behind our drive mode displacement, which again lags behind our applied force. So we've got a significant delay between our force being applied and us actually generating a sense mode signal. All right, so the last thing that I want to do with you guys is work an example problem, showing us how to kind of put all of this stuff together. So half my page will be trying to draw this structure. So I'm going to start with, let's put a proof mass here. In the middle, like so. And then I'm gonna attach a bunch of fingers to this thing as best I can. These fingers will all be attached to some stationary anchor, which I'm going to denote by this big X thing going through it. And I'm going to have, what I'm going to try to make is an identical system on the opposite side. So these are where our drive mode vibrations are going to come from. So we're going to drive this thing left and right. Using these drive mode capacitive cone drive actuator. And now I'm going to draw the kind of support structure for our proof mass here in the center. So that might be something like this. Got some just simple springs connected to this structure. Going to do that on both sides. And then I'm going to attach that structure to some anchors like so. Same thing for the guy on bottom. And then attached to each one of these structures on the top and bottom end, I'm also going to have yet another capacitive comb drive. So something akin to this. And these are going to be my sense electrodes. Let me draw another one of these guys down here on the bottom. We're going to have a second set so we can increase the overall capacitance and get a bigger signal out of this guy. So essentially, what's going on here is our sense mode vibrations, excuse me, our drive mode vibrations are going to be in this direction if our central plate experiences some rotation capital omega, then it's going to induce drive mode vibrations, excuse me, sense mode vibrations in this direction that we can quantify using those capacitive cone drives on the top and the bottom of the structure. So now let's give you guys some values for things. So the mass of the drive mode would pretty much just be that central plate. So let's call that 5 times 10 to the minus 9 kilograms. Our spring constant for our drive mode would be 0.8 newtons per meter, and that's going to be the total thing. Let's say that the number of overlaps for our drive mode is 100 per comb drive. Quality factor of our drive mode is 500. And then our height would be, of each of these electrodes would be 5 microns. The distance between the electrodes will be 2 microns. The length of each of these drive mode electrodes, nominally 20 microns. And then in our sense system, we're going to have a mass of 6 times 10 to the minus 9 kilograms. The spring constant of 3.8 newtons per meter. The number of fingers is going to be 20, or finger overlaps. Let's make it 20 per comb drive, I believe. Our quality factor will be 500. HS will be 5 microns. DS will be 2 microns. LS will be 50 microns. And let's say that the resonator is biased at VDC is equal to 15 volts, and the drive voltage amplitude will be V naught is equal to 1.5 volts. And I want us to calculate the maximum change in capacitance seen by the sense electrodes for an angular rotation of capital omega is equal to 10 radians per minute. Okay, so lots of things going on here because this is a big system and it's going to be incorporating lots of the different things that we have talked about. Okay, so if we go back, we need to just approach this guy kind of step by step, right? So in order for us to figure out what the hell is going on with the sense mode, we need to figure out what the hell is going on with our drive mode system, okay? So we are going to actuate our drive mode at the resonant frequency of the drive system because that is what is usually done. And so we are going to need to figure out what our drive mode vibrational amplitude XD is, which means we need to figure out what that force FD is. Okay. So starting with our force, okay. So our drive mode force, sure, absolutely. Do I need to scroll back up so you can see the thing? Yeah, fair enough. All right. So calculating our force. So this is going back to the lecture on capacitive actuation or electrostatic actuation, where we have a system where we have both a DC voltage and an AC voltage that are going to be applied. So from that lecture, we would find that our force, and I'm going to have a factor of 2 here because there are 2 actuators acting, that we are going to have twice VDC times V naught, the amplitude of our AC vibrations, times ND epsilon H sub D over D sub D times the cosine of omega naught D. Sorry, that shouldn't be a capital D there. Omega naught D T. Like so. From this, the amplitude of our force for our drive mode is going to be 2 times 15 volts times 1.5 volts. Our number of overlaps per comb drive is 100. Epsilon in this case is going to be the permittivity of free space, so 8.854 times 10 to the minus 12 farads per meter. Our height is 5 times 10 to the minus 6 meters. And all of this is going to be over our distance between our drive electrodes 2 times 10 to the minus 6 meters. And when I did this, I wound up getting 99.608 nano newtons. So that is our force, the magnitude of our force. So from this, the magnitude of our drive mode displacements, XD, should be negative J times QD over KD times the magnitude of our drive force. So that's going to look like negative J times 50, because quality factor is a dimensionless quantity, 0.8 newtons per meter times 99.608 times 10 to the minus 9 newtons winds up being negative J 6.225 microns, where once again, that negative J just means that our drive mode displacement is lagging behind our actuation force by 90 degrees north. Oh, I wrote 500 up top and then I have 50 in here. So let's see whether or not I did the math right and made a typo or did both things wrong. Good catch. So minus, actually, let's just do it this way. 500 over 0.8 times 99.608 times 10 to the minus 9. Divide that by 1 times 10 to the minus 6. So that should be 62. Um, all right, so I need to make a fix here because North caught something and it actually breaks everything. So good catch there. So this QD needs to be 50. So let me explain why QD needs to be 50. If it isn't, our displacement is larger than the actual length of our electrodes, which isn't going to work. We're going to smash into the sides of this thing. So let's make that guy QD 50. That's 50. Sorry about that. And then negative 6.225 microns, which is an acceptable amount of vibrational amplitude. So my apologies. Thank you for that catch, North. For right now, I'm just changing QD. Now I'm worried about the rest of these numbers, but it'll be okay. We'll sort it out. So omega naught D, the resonant frequency for our drive mode, would be the square root of KD over MD. And when I calculated this, I got 12.649 kiloradians per second. And omega naught S, I got to be KS over MS, square root of that, 25.166 kiloradians per second, which means that these are not matched because they're not the same. But since omega naught S is only roughly twice as large as omega naught D, I wouldn't really count it as separated modes either, which means we would have to rely on our actual full transfer function to calculate XS, okay? So I'm just going to put not matched and not separated here. So So let me show you something first, and then we'll talk about that. Okay. So if I just use my full-on transfer function here, so -1 over m sub s twice md xd capital omega naught d squared omega naught s over qs all over omega naught s squared minus omega naught d squared. Just to be clear here, all I'm doing is substituting in omega naught d everywhere I had omega, because that's the frequency that we're exciting this thing at, plus omega naught d, omega naught s over qs. Both of these terms should have been squared, minus j twice md xd capital omega naught d omega naught s squared minus omega naught d squared all over omega naught s squared minus omega naught d squared quantity squared plus omega naught d omega naught s over qs squared. Close this thing off. When I threw this into MathCAD, I got 13.863 with an angle of 0.771 nanometers. So this phase angle here is just telling us by how much our sense mode displacement is lagging behind our drive mode displacement here. Okay. Now, just for what it's worth, and this is why I told you to wait just a second, if our modes were matched, our sense mode displacement would have came out to be J 1.031 microns, excuse me, yeah, J 1.031 microns. And with separated modes, I would have got my displacement to be 10.362 nanometers. This guy right here is actually pretty damn close to what we calculated, right? Our phase difference is only 0.771 degrees, whereas in a match mode, our phase difference was 90 degrees. So it would be 90 minus 0.771, or about 89 degrees. The amplitude of this guy, 10.362 nanometers, is relatively close to the calculated 13.863 nanometers. So realistically, if if omega naught s is 3 to 5 times larger than omega naught d, that's enough for it to be considered separated. So we're really right on the edge of being able to call these guys separated modes based on what our displacement looks like there. So, anywho, so we've got our sense mode vibrational amplitude. And so from that, we need to be able to figure out what our capacitance is, because that's the ultimate goal here, if I'm remembering correctly. Calculate the change in capacitance seen by the sense electrodes for that particular rotational speed. So, excuse me, our nominal capacitance with no, let me call this C naught, comma, sense. So this is with no displacement whatsoever. This would just look like twice ns epsilon hs ls over ds. Actually, I'm going to change this to 4 just because up here I said that this was 20 per comb drive, and I see 1, 2, 3, 4 comb drives. So I'll just fix that. And so that's going to come out to be 88.542 femtofarads. Pretty damn small, but just because there's not a whole hell of a lot of fingers here. When our device is actually experiencing vibrations, right, we are going to have two systems where we would have NS epsilon naught HS LS times 1 over ds plus XS plus 1 over ds minus XS, right? Because as our sense mode vibration goes up, these two guys get closer together, these two guys get further apart. So we're going to have one capacitance that's increasing in parallel with one capacitance that's decreasing. That's what these guys look like. And then this factor of 2 here is from the fact that we've got one of those systems on top and one of those systems on bottom. And so just doing simple math here, this would come out to be 88.546 femtofarads. And so our change in capacitance is literally a whopping 4-ish, 4.252, just doubling what I had previously, attofarads, or 10 to the minus 18 farads. So not a huge change in capacitance that we're seeing off of this guy. Couple of different reasons. One, not a lot of fingers in our sense drive. 2, our rotational speed was 10 radians per minute, right? So that would be if we spun our phone 1.5 times in a minute smoothly. So we shouldn't expect to see a huge amount of signal on that because it's fairly slow. If we bumped this guy up to a radian per second or something like that, we'd see a much larger amplitude. Anyway, so that is a example problem showing you how you would do calculations related to a capacitive gyroscope.